it's the pause that gets me. I think you know exactly what I'm talking about. Or maybe one of those new Study Buddy apps. And it's going great. The responses are snappy, the tone is witty, and you actually feel like you're being understood. And then you stop, you look at the screen and have this sudden creeping thought, wait, am I talking to a person or did I just pour my heart out to a server farm in Oregon?
It's basically the modern Turing test, but it's happening to us every single day. We used to talk about the uncanny valley with like robot faces, how they looked almost human but just a little bit wrong. Well, now we're living in the uncanny valley of text. That friction between what feels human and what we know is just silicon, it's disappearing.
That's the thing. It's not just disappearing. The line is practically gone. And that's what we're really digging into today. We're not doing the basic what is AI thing. I think everyone listening knows what ChatGPT is by now. We want to go deeper. We've got a stack of research here on what we're calling the mechanics of chatter. We want to understand why the machine sounds so much like us.
To do that, we really have to unpack the two massive pillars that hold this whole thing up. First, we need to talk about human-like language generation, so the mechanism itself. And then we have to get into scalable language models, the sheer size of the architecture that makes the magic trick work.
I like this approach because I feel like so much of the coverage is just breathless hype. It's all the robots are coming or AI is going to cure everything. But very few people stop and ask the engineering question, how does a box of math know how to be sarcastic? I mean, sarcasm requires a theory of mind, right? You have to know what I know and then flip it. How is a machine doing that?
Yeah, that is the million-dollar question. And the answer is, well, it's going to be a little disappointing to the mystics, but fascinating to the engineers. It isn't magic. It's not consciousness. It is a very specific combination of high-dimensional math, an insane amount of data, and just a fundamental shift in how we approach computing.
So the mission today is to strip away the illusion. We want to see how these models went from being tools like, a hammer or a calculator to what the research is calling partners in communication. That's a heavy label. Partner implies a two-way street.
It does. And to even understand why that label is on the table, we have to look at that first pillar. Human-like language generation. We need to contrast let's call it the old world of computing with the new one.
Okay, let's set a baseline. When you say old world, we're not talking about like abacuses. We're talking about the internet of, say, 2015.
Correct. Until very, very recently, computing was all about retrieval. It was deterministic. You put X in, you get Y out. Every single time. If you went to a search engine or an old chatbot and typed, "What is the weather?" the computer was acting like a librarian. It just ran to the weather aisle, grabbed the data for your zip code, and showed it to you.
It was just fetching.
How about?
Temperature, 72, wind, 5 miles per hour. If I asked it 10 times, I got the exact same line 10 times.
Exactly. And that's useful, but it's not a conversation. Now look at the generative approach. When you ask a modern large language model about the weather, it's not just fetching a row from a database. It is constructing a narrative. It might look at the data 72 degrees, sunny, and then it looks at the probability of how humans describe that kind of day.
So it generates something more like, it's a gorgeous 72 degrees out there, probably a great day to skip work and go to the park.
Right. And this is where people get confused. They think the AI knows it's a nice day. It doesn't. It doesn't have skin to feel the sun on. What it does have is a mathematical model that says when the data is 72 degrees and sunny, the statistical chance of a human using the word gorgeous or beautiful goes up by, say, 85%. It's just predicting the sequence of words that best fits the pattern.
But wait, hold on. If it's only predicting the next word based on math, why does it feel so fluid? My phone's autocomplete predicts the next word, and that thing is a disaster. If I let autocomplete write a sentence for me, it sounds like a drunk toddler. Why is this so different?
That's a great distinction to make. Your phone's old autocomplete is looking at a very, very short horizon.
Yeah.
Maybe the last 2 or 3 words you typed. It has no memory of the paragraph you wrote 5 minutes ago. Modern models operate with a huge context window. It's not just looking at the last word, it's looking at the entire conversation, the tone, the instructions, everything, all at once.
So when I'm being snarky to the bot and it gives me some dry wit back, it's not because it gets the joke.
No. It's because in the billions of sentences it was trained on, snarky input is very often followed by witty retort. It's just completing the pattern.
You've just hit the nail on the head. It's the world's most advanced pattern completion engine.
Exactly. It's ingested libraries, websites, court records, movie scripts. It has learned the shape of a sarcastic argument, the shape of a poem, the shape of a technical manual. It's all probabilistic. It just calculates. Given this input, what is the most statistically probable next step? to satisfy the user.
Which brings us back to that shift from tool to partner. If I'm using a tool, I want reliability, the same answer every time. But if I'm brainstorming or if I'm a student looking for a tutor, I don't want a database dump. I want that fluidity.
And the research points to 3 big areas where this partner idea is really taking over: creative writing, customer service, and tutoring, which makes sense. In those fields, the correct answer isn't a single data point. It's a vibe, an explanation.
The tutoring one is fascinating to me. A good tutor doesn't just know the answer, they know how to rephrase it until you finally get it.
And that's the style transfer capability. You can tell the model, explain quantum entanglement to me like I'm a PhD student. And it uses one set of probabilities, jargon, math formulas. Then you say, okay, now explain it like I'm 12, and it just swaps the probability distribution. It drops the jargon. It picks up analogies about coins or socks. Same information, but the delivery mechanism completely changes.
That flexibility is incredible, but it feels like we're glossing over the hardware reality here. You can't run this kind of math on a pocket calculator. Which leads us to the second pillar, scalable language models.
This is the engine room of the whole discussion. We have to talk about scale. And I don't just mean big. I mean numbers that are genuinely hard for the human brain to visualize.
We hear the word parameters all the time in the news, right? This model has 7 billion parameters. That one has 1 trillion. I think for most people, that's just noise. What even is a parameter in this context?
Okay, let's strip away the jargon. Imagine a giant sound mixing board, in a recording studio with all those knobs and sliders.
Sure. You turn the bass up, turn the treble down, that kind of thing.
Right. Now imagine that mixing board doesn't have 50 knobs. It has 100 billion knobs. Each one of those knobs, each parameter, is a tiny weighted connection between 2 concepts. One knob might control the strength of the link between the word king and queen. Another might control the link between apple, the fruit, and apple, the company.
So when we train the model, we're basically just twiddling these billions of knobs until the output sounds right.
In essence, yes. Training is just feeding data through the system, seeing where it gets it wrong. Oh, it predicted apple, the fruit, but the context was iPhone. That's an error. And then you just slightly adjust all the knobs to fix that error. When you have 1 trillion parameters, you have 1 trillion of these tiny nuanced connections that build this incredibly high-dimensional map of human knowledge.
And this is where the scale part is so critical, because a small model, let's call it the sketchy map version with only a few billion parameters, might be great at one thing, like it might be trained only on medical texts, so it knows everything about biology.
But if you ask that small medical model to write a poem about mitochondria in the style of Eminem, it just falls apart. It doesn't have the parameters that link cellular biology to hip-hop rhyme schemes. The map is just too small.
Yeah, the source material had a great comparison here. It contrasts asking about astrophysics with 18th century literature.
That is the perfect illustration of scale. Imagine you ask a model, compare the gravitational pull of a black hole to the social gravity of Mr. Darcy in Pride and Prejudice.
That is a ridiculous question. I love it.
It is ridiculous, but just think about what's required to answer it.
Yeah.
The model has to understand general relativity, dense mass, event horizons, all that. And it also has to understand Austen's Regency era, social dynamics, wealth, status, the inescapable pull of social expectation.
A smaller model would probably just crash, or it would hallucinate and say, Mr. Darcy is a star.
But a scalable language model 1 with those trillion parameters has read the physics textbooks and the Jane Austen novels. And crucially, it has seen enough human conversation to understand the concept of a metaphor. It can find a path on its map from black hole to social pressure because it has enough connections to bridge those 2 very distant islands of knowledge.
So it can say something like, just as light can't escape a black hole, Elizabeth Bennet can't initially escape the social gravity of Darcy's wealth.
Precisely. That insight, that ability to connect 2 totally unrelated fields is a direct result of scale.
Yeah.
You only get that kind of emergent intelligence when the model is big enough to hold the context of all of human culture in its weights at the same time.
Which connects back to the practical uses, right? Like real-time translation. It's not just swapping hello for bonjour. It's understanding the idiom, the culture.
Yeah, if you translate an American idiom like, it's raining cats and dogs, literally into French, people will think you're crazy. A scalable model understands the meaning behind the phrase heavy rain and swaps it for the French equivalent, which ironically translates to it's raining ropes. You need massive scale to capture all that cultural nuance.
Okay, so we have this godlike mixing board with 1 trillion knobs. It writes poetry, it solves physics problems, it translates idioms, sounds perfect. But I'm looking at the challenges section in our research, and I'm seeing a lot of red ink.
There's always a cost. We have to do a reality check here. And the first cost is literal energy.
Right. We think of the cloud as this weightless, ethereal thing. But these parameters are physical. They live on
They
chips.
live on massive clusters of GPUs in data centers that consume the power of small cities.
Mm.
Every time you ask your partner to write a funny poem about your cat, billions of calculations are firing. That generates heat. It consumes electricity. This is high-cost intelligence. We are literally burning resources to generate text.
That's a sobering thought. But there's another cost that the research highlights, and this one feels a bit more insidious. The bias problem.
This is an almost unavoidable consequence of how these models are built. Remember, we said they're trained on libraries, websites, the open internet.
And the internet is, well, it's the internet. It's full of trolls and stereotypes and historical prejudices.
The model is a mirror. If the training data contains historical biases, like if 80% of the text mentioning doctors use he and him, and 80% of texts about nurses use she and her, the model learns that statistical correlation. It doesn't know it's a stereotype. It just looks at the math and says, doctor usually equals he.
So if you aren't careful, you can end up with a trillion-dollar supercomputer that's also a misogynist.
Or a racist, or politically biased in one direction or another. This is why alignment is such a huge field of research now. Engineers are trying to go in and, tune the knobs by hand to counteract those statistical biases. But it's incredibly hard. You're fighting the weight of the data itself.
It creates this weird tension. We want the model to be human-like, but we only want it to be like the best version of humans, not the worst. And the data contains both.
That is the core conflict. The model is an aggregate of humanity. Cleaning that up without breaking its ability to understand the world is a massive, massive challenge.
But despite the energy bill and the bias issues, the source material does end on a pretty optimistic note about opportunities. The consensus seems to be that the utility outweighs the risk, for now.
The leverage is just too high to ignore. The research pivots to the main beneficiaries, students, businesses, and content creators. We're looking at a huge acceleration in just efficiency.
Right, we talked about efficiency for businesses, automating customer service, summarizing documents. That's the save money side. I'm more interested in the make new things side.
Think about the blank page problem. You're a writer, a coder, a strategist, and you're just staring at a blank screen. That's a high friction state to be in. These models can eliminate that. You can use the AI as a sounding board. Give me 10 ideas for an intro. Critique this argument. Refactor this piece of code.
It just raises the baseline of competence. You don't have to start from zero anymore. You can start from a pretty good draft.
And we are really just in the dial-up era of this technology. The models we're using today, the ones that are amazing us, they're going to look quaint in 5 years. We're just starting to figure out how to integrate this scalable intelligence into our workflows.
The dial-up era, that's wild to think about. We're sitting here amazed by the magic trick, and you're saying this is just the grainy, buffering version.
We haven't even seen the broadband version yet. As the hardware gets more efficient, as the models get better at reasoning, not just predicting words, but actually checking their own logic, that partner dynamic is only going to deepen.
Okay, so let's try to wrap this up. We have covered a huge amount of ground. We started with that weird feeling you get from a text message that feels a little too real.
We broke down the mechanism, human-like language generation. It's not a ghost in the machine. It's a probabilistic engine calculating the best next move.
Then we climbed the mountain of scalable language models. We saw how billions of those little weighted knobs let the system connect astrophysics to Jane Austen.
Giving us that context and nuance.
And then we looked at the bill, the energy costs and the data biases that come from training on, well, the raw output of human history.
But ultimately, what we're looking at is a fundamental shift in how we communicate. We're adopting a synthetic partner.
A partner that knows everything we've ever written, but understands none of it.
Exactly.
That leads me to one final thought I want to leave everyone with. We keep using this word partner in any real partnership. A marriage, a business, the partners influence each other, right? They rub off on each other. You start using your friend's slang. You start thinking like your business partner.
That's true. Convergence is natural.
So here's the question. If we are spending hours every day talking to these models, and these models are trained on our data, but now we are generating new data with them, what happens to that loop? Are we shaping the AI, or is the AI starting to shape how we talk and think and write?
If you start seeing your friends talk in perfectly structured bulleted lists,
Yeah.
you might have your answer.
Something to think about. That's it for this deep dive into the mechanics of chatter. Thanks for listening.
See you next time.